Okay. Yeah, I think I'm ready. If you want to start. Great. All right. Hi, everyone. Welcome to day 5 of our Poly course. I hope you enjoyed, if you saw it, David Jazz's guest lecture yesterday. But we're going to continue on. And today is kind of just going to be a mix of sort of miscellaneous kind of categorical properties of the category poly that we haven't covered yet. And some of these are possibly applicable to dynamical systems, the dynamical system story that David talked about. Some of these are going to show up, or we're going to mention them in later parts of the course. And some of these are just kind of interesting, and we wanted to highlight them. And there's, yeah, so we're going to cover, it's going to seem a little bit all over the place, although I'll try to connect each of these to each other. And also some of these we don't really know necessarily, or like David and I haven't like really sat down and thought about maybe how they contribute to the dynamical systems picture or how they contribute to the decision-making picture. And so if you have thoughts on these, or like if you get like ideas, we'd obviously really be excited to hear about them. So yeah, and then there's also some things where like the notation or the name we have for them are maybe not sort of exactly what we want yet, and we're still trying to pin that down, and you'll see a little bit of that today. But hopefully this will still be a coherent narrative. Yeah, so let's start off by something or just another way of thinking. I think David already kind of alluded to this, but just thinking about these sort of polynomial functors and the morphisms between them as this sort of general way of thinking about dynamical systems and interfaces on them. And so we already talked about how a monomial, when we have a monomial of the form ay to the b, we can think about it as as the interface of a dynamical system that gives, that spits out elements of A and takes in elements of B. And specifically, once we stick a state system in front of this, that looks like sy to the s, it's going to, the state will tell you what elements in A it spits out, and then whatever element in B is put in, that, along with the current state, is going to give you a new state that this system updates to. And we can generalize this to these kind of general polynomials with, it's a similar structure, except this picture isn't sort of the most accurate thing, right? So this is a polynomial that gives out, it still spits out outputs, and its outputs, its possible outputs are just its positions. And the inputs it takes in actually sort of depend on whatever output it spits out. And so this is how we're going to draw these, at least for today. But really what you want to think about this as is like the output it's giving out is like changing the entire shape of this box. And it's changing sort of like the kind of things that can go into this box, right? Like maybe it changes into a square hole or a round hole, and then it only lets specific kinds of things in. And then there is some sort of input dependent on sort of what the output is. So I might just draw a dashed line like this. But that's just to indicate there's this sort of dependency going on here. But you can still sort of think about this as like these boxes with outputs and inputs, and I'm going to draw them like this today. And in fact, if you draw them like this, you can think of a morphism as a way of wrapping a bigger box around a smaller box, which is why I call these wrapper interfaces, right? Yeah, so yeah, the idea is that you have a dynamical system, and you have a way it interacts with the world. It takes in inputs, it gives out outputs. That's its interface. But you can actually put another interface around this system, and sort of like, it's kind of like, if you're familiar with like an API, right? It's an interface you put around the smaller interface that interacts with this inner interface in a particular way, and then whoever's interacting with the whole system only really sees the outer interface, but is actually still interacting with the internal system. Yeah, and right, so the way we can think of a morphism from a polynomial P to a polynomial Q, we've talked about this a few times, but just to review, it's a function on the positions from the positions of P to the positions of Q, and then a function backwards. It's kind of this dependent function, or you can think of it as a family of functions. Given each position of P, it's a function backwards from the directions of Q at the position of Q that this phi of 1 sends it to, back to the original directions at that original position of P. And so the way you can see this visually with our wiring diagrams, or like slightly modified wiring diagrams, is that when P gives out an output, it's an element of P of 1, and it goes through this little triangle, which I just think of as a function. It sends any input or any sort of element of P of 1 to some element of Q of 1. So it's converting outputs of P into outputs of Q. But at the same time, it's sending this output of P back over here, which is sort of indicated by this here. And so whenever you put an input into this larger box, it takes that input together with whatever output of P it gave and passes it through this triangle to tell you what to input inside the smaller box P. And so this is a kind of sort of organized way for the outer interface to interact with the inner interface. And so we can think of all our polynomial morphisms like this. Yeah, and so I think the last thing I'll say about this is that, yeah, it gives us this way of thinking about just interfaces of sort of any system, right? Like, because you can think about, you can think about sort of a user interface where like someone comes along and like receives outputs from this P, but then also puts in inputs here. Or you can think of another system kind of wrapping around this, like, and then that's the thing that puts in inputs and gives out outputs. And really these two perspectives, if you think of any kind of system as, if you think of any agent as one of these, having one of these polynomials as its interface, these are really just the same perspective. Yeah. Now, if we're talking about a system, at some point we're going to need to end somewhere, right? Like it needs to, or usually, maybe not. Maybe we can keep it open, but we also want to think about sort of how to think about a closed system, right? And what I mean by that is here we actually have some like choices to make, right? We can put sort of anything in here right now. But the one thing we know is that the thing that we put into here has to sort of be compatible with whatever comes out of here. So it has to be a direction at whatever position this is. And so I guess what I'm trying to say here is that eventually we can think about if we have a closed system, it's as if we're wrapping a polynomial around with a closed box without, with sort of no inputs and no outputs. Although when I say no inputs and no outputs, what I really mean is that there's sort of exactly one possible output and there's exactly one possible input. And so what's a box that has exactly one possible output and one possible input? It's just y, thank you. Yeah, and so we can depict a morphism from, let's see, from an arbitrary polynomial P to y. I'm going to draw it out in a second, but let's see. Yeah, so right, so this is going to be a morphism from p to y. And what's it going to do? Well, if there's no inputs or if there's no outputs coming out of this box, we don't really need this function here. So this is basically the same thing as saying, right, like all of the positions here go to the same position here. So that's like nothing's really happening there. And so the interesting thing is actually this backwards movement where each position of p comes over here and gets assigned a direction at that position. And without any other inputs here, that's just going to, if we redraw that, ignoring this portion and ignoring like anything going in, that's just going to look something like this, right? It's just for every element of p of 1, we assign it an element of p bracket I, where I is that element of p of 1 that we picked. Yeah, and so we can think about what this kind of thing really is, right? So maps in Poly from p to y are just assignments for every element of p of 1, we give it an element of p bracket I, and we can think of that as this sort of as this kind of dependent product here. Yeah, and we have a special name for these. We also have a special notation for these. We're gonna use gamma of p to mean this the set of maps from p to y, and so these are assignments of directions for each position. Let's see, and there's a couple of ways we can think about this. One is this is really just a section of the projection. If you remember way back in the first class, we thought about, also kind of David Jazz yesterday, we thought about polynomials as these projections from the directions for each direction, assigning it to a position. This is just one of the sections of this map that sends each position to some direction that's at that position. We can also, let's see, so David likes to call these maps situations, because really if you think about it, it's it's assigning for each, if we again see the Corolla picture, it's assigning for each position that you could be in. If you're standing in some position, it's giving you some direction to face, right? And so this is kind of a situation that you could be in. Any sort of output you give gets met with an input back. Yeah. And I also like to think of these as enclosures, because if you look at this picture, it's just, we're kind of just boxing everything in, right, to this closed system. So we're kind of, this is like an enclosure of P. It's a way of closing up this open system, right? Like if we wanted to enclose this, we would just connect this loop here, and that would just be mapping this to Y. Yeah, I'm gonna, any questions at this point? I'm gonna take a sip of water, but, yeah.
Do you mean something else in the middle here with P1? I don't know.
Sorry, yes, this is a notation I introduced on the first day, so it's a little weird, but P dot 1 means,
Oh, yeah, right.
sorry, there's a dot on top of here, and it means the set of all directions of P. And the reason for this notation, it's a little weird, but it's the derivative of P. If you think about taking the derivative of the polynomial and then plugging in 1, it actually spits back the set of directions. Yeah. Okay. Now, one thing that becomes interesting is when we think about enclosures of multiple systems. So I'm actually going to, yeah, I'll just draw it here. So if we had two systems next to each other, P and Q, and think about, and so this would be, let's see, so this would be P tensor Q. And so if we think about one possible way of sending p tensor q to y, well, what that means is, well, the positions of p tensor q are just pairs of positions of p and q. So they're pairs of outputs of p and q. So instead of just one of their positions, we're sending each of their outputs, a pair of their outputs, to this function here, represented here. And I'm actually going to, instead of a triangle, I'm going to try to draw, let's see how my drawing ability is. We're going to draw a little trapezoid here because we can think of this output as also two outputs, right? It's going to be a direction of p at the position we sent in and a direction of q at the position we sent in. Draw a few arrows on here to remember how the flow goes. Yeah, and so this would be a map from p tensor q to y. And I'll just draw a big box around here to remind us that we have wrapped it with an interface y. Yeah, so how do we want to think about this gadget here? Well, one way we can think about it, so you can think of this as two systems, right? Like they both have maybe a system inside them, or just sort of like driving them, but they're two interfaces in the same environment. But you can also think of this from the perspective of maybe just one of these interfaces. So for example, if we fix, let's see, how do I want to do this? If we fix an element of p of 1 here, if that's fixed, right, and then we also ignore what's happening to p for now, and look at what happens to q. Once we have a fixed element of p of 1, this little trapezoid in the middle is just sending positions of q to directions of q at that. And so this, right, once we fix p of 1, what's happening here is just an enclosure of q. Right, it's just a map from q to y, just like that one. And so there's, let's see, yeah. And so in some sense, there we have a function that sends every fixed position of p to an enclosure of q. Now, I'm just going to omit the parentheses here. Now, something symmetrical is happening on the other side. Once we fix if we fix a position of q coming out of here, and we've already dealt with what's happening here, so really this trapezoid just becomes an enclosure of p. And so we are also assigning for each position of q a enclosure of p. And so in fact, we have this isomorphism here. And really what you want to, like intuitively how you want to think about this is if p and q are in the same situation, you can also think of p being in a situation that includes q, that includes whatever sort of output q is giving out. And also q is in some situation that includes p, that's affected, dependent on whatever output p is given out. And yeah.
Nelson,
Yeah.
asks, can you do an example? So maybe fix a p and q and show, and like,
Yeah.
gamma p tensor q and the other ones?
Yeah, let's see. Okay, let me pull up. Sorry, just banged on my mic. Let's see, let me do 2y, let's do 2y squared tensor, let's say y cubed plus, no, I can't have a 1 here. Y cubed plus y, yeah. So yeah, and I'm going to draw that out. So draw out. So here we have 2y squared. This is kind of like how I drew it on the first day. And down here, this is 2y squared. This is y cubed plus 1. And so we can think of this, let's see, yeah, so we can think of first of all, we can think of their tensor as something with 4 positions. This one has, I'm just going to draw these directions and dots. This one has 6 directions. This one has 6 directions. This has 2 times 1. This one also has 2 times 1. And picking an enclosure for P tensor Q is just picking a direction for each position. It's kind of like a direction field on this kind of thing. So let's say we pick this one, this one, this one, and this one. And now, but really we could have also thought of that as for each, so for each position of P here, so for each row here, we pick a direction, we pick an enclosure of Q. And so we are picking, for this row, we're picking this one and this one.
Would you be willing to draw your 2 dots vertically instead of horizontally?
That's a good idea. Let's see. Yeah, that's a good idea. Yeah, so for this row, we are picking this direction and this direction. And then for this row, we are actually picking this direction, so this third direction, and still this same direction. And so that kind of tells us it's going to be somewhere here, somewhere here, somewhere here, and somewhere here. And then the other thing we need to do is for each position down here, for each column here, picking one or the other, or picking an enclosure on this whole thing. And so for this column, we are actually picking so this second one and this first one, which tells us these 2 directions. And then for this column, we are picking this top one and this bottom one, which tells us those 2 directions that we want. And yeah, and you can try to work this out. But yeah, that's how that, I hope that answers that question. Yeah. Okay, any other questions about that? Okay, so this perspective may or may not remind you of something. And what I mean is this way of looking at, right, so we have sort of 2 perspectives on this, what's happening right here. We can either think of these P and Q as tensor together, so right next to each other in the same system, or we can think of things sort of from the perspective of P, what's happening to P. We can think of Q in addition to Y as sort of part of this wrapper system, as opposed to P and Q together, internal in the system, and sort of Y wrapping around it. And this is actually, I'm actually going to erase this example. This might remind you of the idea of closure. So we're going to talk about the closure of this parallel product, this tensor product that we have. And yeah, so the idea is that if we have a map out of, let's see, yeah, if we have a map out of P tensor Q to maybe some general polynomial R, can we also think about this as some wrapper on just P? Can we think about Q as part of the environment wrapping around it? And so what we want here is something that doesn't depend on P, like we can just sub in any P here, only depends on the actual things in the environment. outside of it, so Q and R. So is there some bracket, some Hom bracket Q comma R that gives us this natural isomorphism? So let's look at that. If we draw this out, what's going on? So I'm going to draw a picture like this, except more like this, because we actually have an open box around our system now. So we have a box P. I'm going to try to draw the boxes a little smaller so we can fit everything here. Box P, a box Q, tensor together with a box R outside. P is sending some sort of output, and Q is sending, they're sending an output as a pair out this way to R of 1. So this is something from P of 1, something from Q of 1. But they are also sending, they're reminding us back over here of what these outputs are, which is going to affect, this pair together is going to affect what we update, this sort of update function here. So when we feed in a direction of R corresponding to whatever position came out here, make sure I got this picture right. I'm going to make this a trapezoid again because we need, we're going to feed an input into P and then feed an input into Q. P bracket I, Q bracket J. Okay, so this is our picture here of what's going on. Let me add some arrows here to help. Yeah, okay. And now, what I was asserting is that there's some sort of way to think about this instead of as R wrapping around P together with Q, as Q and R together wrapping around P. So let's isolate P from this diagram here. I'm actually, what I think I'm going to do, hopefully you have this picture, I'm actually going to erase, sort of separate out P here, because anything could go here, and kind of highlight the connections that it's making. So there's sort of something it's feeding in here, something it's, and then something that goes in here. And somehow we want to figure out what Q bracket R should be. Okay, let's look at this picture over here again. And remembering that whatever the positions of the interface we wrap around are, they should be sort of the, whatever comes out, it should be the set of things that could come out of this once we plug in an input, or once we plug in an output of our inner interface. So here, when we plug in something here, and here it's just an element of P of 1, when something here goes along these two paths, what happens, right? Like, what kind of thing do we make? Well, once we fix whatever goes into the sort of outward orange arrows here, that gives us, first of all, actually, yeah, let's look at what it gives us. Well, it gives us something, this triangle here really just becomes a function from Q of 1 to R of 1. And then this trapezoid, once this is, if we ignore sort of what's coming out of it to P, and we fix what's coming into it from P, it's a function that takes in some input of R that was dependent on whatever, so K is whatever came out of here, and takes in this input of Q, this output of Q, and gives you an output, gives you an input for Q. And this thing here, if you just sort of like redraw it, like it's really just this. It's a wrapper, right? It's a wrapper around Q. It's R wrapped around Q. It specifies a wrapper of Q. So the positions of Q bracket Q comma R are just morphisms from Q to R. And so that's what it spits. That's what each position of P spits out. Now the directions of this thing is, if we again remind ourselves what directions should be, it should be whatever we're able to put in here, which taken along with the output of P gives us an input for P. And so we can locate that here. On this diagram, we're putting in an input of P, putting in an output of P, and getting an input of P, sort of in this part here. And what goes in with it is something on this thread here and something along this thread here. And that's going to be a position of Q and a direction of R. Except not just any direction of R, so it's a position, it's an element of Q of 1 and an element of R bracket K. But this K specifically came from over here. It's whatever position of Q of 1 we fed in here to get a position of R of 1 via phi, put inside these brackets here. It's those directions. And so this thing is going to be a position. We pick a position of Q, and then we pick an element of R bracket using this phi to give us a position of R. That's,
Direction.
Oh yeah, the whole thing is a direction, right? Sorry, I meant this is a position of R, and then it gives you, so it's a position of Q, and then a direction of R at whatever this phi sent us to. And you might need to stare at this diagram a little bit and see how this gives you that. But that is the formula for the parallel closure. There is a different way of writing this, which we introduced first in the book. But this is how, I think this is the way you can see sort of that like pops right out of this. OK. Cool. Any questions there? Yeah. Yep.
Why are the positions the polymaps from Q to R instead of just the functions from Q of 1 to R?
Repeat the question.
Yeah, so the question was, why are the positions actually polymaps from Q to R as opposed to just functions from Q of 1 to R of 1? And that's a great question. And it has to do with the fact that there's more being outputted into this, like out of this diagram, right? Like if we only put that here, that doesn't account for this wire here, right? There's something coming out of this wire here that actually only depends on whatever is coming out out of P here, right? And the rest of everything that doesn't have to do with P. And in fact, sort of this wire here, if we fix an element of P of 1, it's just whatever direction comes out here that's given by the position of Q and then the direction, the corresponding direction of R. And so that's exactly, so this part of this is exactly sort of this part of this diagram. And so that's the backwards function. And that's exactly what you need to give that backwards function here to give that full morphism from Q to R. Does that make sense? It's a little weird, right? I acknowledge that it's a little weird because you don't think this thread should have anything to do with that because it doesn't on this picture here. But that is how that translates. Yeah.
The right-hand one, the right-hand orange is sufficient to determine the left-hand trapezoid on blue.
Yes. Yes, exactly.
And the left-hand trapezoid, the bluey part there, is the rest of that on right.
OK. Now I'm going to attempt something more daring, which is to apply the same process to figure out a different closure, namely the Cartesian closure. And so I claim that there is also some construction on Q and R that gives a natural isomorphism like this. And we're using this exponentiation notation, but this will very much not be what you expect a polynomial raised to a polynomial to be, but we're just using this as the notation for Cartesian closure for now. Yeah, and so this is actually going to be a very similar diagram to this, because remember, the only difference, P times Q and P, tensor Q have the same positions. The difference between them is their directions. So I'm going to draw this out as I guess as I remind you that the directions of P times Q for any pair of positions of P and Q is actually going to be a sum of directions of P and Q. So it's going to be either a direction of P or a direction of Q at those positions of that pair. And so the output part of the diagram looks the same. So this is P of 1, Q of 1. But what happens at the input is, I don't know a better way to draw this other than to draw it as a kind of switch. So we're still feeding this back here and feeding this back here. And so whatever it takes, whatever direction of R we get here, and also the position of P and the position of Q, and then gives you either a position, either a direction of P, or a direction. I'm going to cross these arrows, which is unfortunate. Let me put that there. Or a direction at Q, and I'm just going to write like an or here. And you should think of this as like sort of a kind of like a switch, that can, like a hinge that can go up or down depending on what inputs it gets here. It's either going to spit something to P or it's going to spit something into Q. P bracket I or Q bracket J. Now you can see already that this, by the very nature of it, is harder to draw, and so it's going to be a little more complicated than this picture here. But we can try to apply the same kind of thinking. Let's see. Let me try something slightly different here. Hopefully these colors will be different enough. So we are going to isolate the output from P. So I'm going to erase these arrows that are coming out of P and just draw them in a different color. Oh. Okay, I got black on this orange. And then I'm actually going to just erase the P because, again, anything could go in that spot. And then also isolate the input here. Let me use red for this, which I apologize for viewers at home if these are hard to, the colors are hard to distinguish. Yeah. Okay. So now let's think about what output results when we fix an element of P of 1. So what happens is we are still spitting out a function from Q of 1 to R of 1. That doesn't change. So we have, so we have a function, I'm going to call this psi sub 1, from Q of 1 to R of 1. But here, what we get here, if we ignore the red, this orange, once we fix something along this orange, this is a function taking in an element of Q of 1 and an element of R bracket K, where K is whatever came out here. K is whatever came out here, but we're only sometimes giving an input of Q, right? We're only sometimes giving an input for Q, because remember, this is a switch. For some of these, we're not going to give anything. It's just going to disappear this way. For others, we're going to give you a direction of Q. And so it's going to be this sort of, right, so if we wanted this to be a polynomial morphism, we would want something of the form, let's see, R bracket psi of j, so psi sub 1 of j, really, to Q bracket j. But this is not actually what's happening. We're actually only giving you only some of these directions for each j are going to give us directions in here. So we're going to actually break this process down into two pieces, right? Because remember, this whole thing would be an element of this. It's a sum over functions from the positions of Q to the positions of R, and a product over the positions of Q, right? For each position j of Q, a function this way. So from, so I guess into Q bracket j from R bracket psi sub 1 of j, right? But again, we don't actually want all of these. So instead, let's think of this instead as a polynomial morphism so we only want some of these. So we're going to isolate out a subset of these directions of R for each position of Q. And so the way we're going to do that is by thinking of this as this new morphism phi as a morphism from Q of 1 y squared into R. And what this is doing is it gives you the function from Q of 1 to R of 1, but then for each position of Q, it's giving you a function back on directions that sends some of these directions to one element, let's call it 0, and then some of these other directions to another element, we call it 1. And we're only going to send the ones to, only going to give the ones a direction of Q over here. And so we do that, and then instead of giving all of the directions of R here a direction of Q, we replace this with a subset of R bracket, let's see, phi sub 1 of, R bracket phi sub 1 of j, which is just everything that gets mapped to a 1 via phi. Actually, let me write it. This is not how I wrote it here, but I will write it like this. So R bracket phi sub 1 j sub 1. So everything in here that gets mapped to 1. Yes, 1 is an element of 2. There are 2 elements of 2, and they are going to be 0 and 1, and that's actually going to correspond to the 2 positions of this switch. So I'm actually going to take this over here, and let me just write it in black. I'm realizing that this might be the only thing I get through today, but that's okay. So this is going to be a sum of this morphism from Q of 1 y squared into R. But then also we have to do this product here, which gives us this partial kind of map on directions here. So over J is in the positions of Q, from Q into Q bracket J from only the elements of R bracket phi sub 1 of J that get mapped to 1. Okay, so that's the set of positions of this thing. That's the thing that comes out when you plug in an element of P of 1. The things that go in, right, like what goes in to give us this element of P bracket I along with an element of P of 1? Well, it's actually, again, going to be very similar to this, right? Because it's going to be an element of R bracket K as well as an element of Q of 1. Except it's, again, it's not going to be every pair of those. It's going to be only the pairs of these that we didn't already divert down here. And so it's going to be a sum that looks very much like this, except it's only these. It's only the ones that get mapped to 0 by this map phi here. Let me draw a line separating this here. And yeah, and so this sort of like very kind of complicated looking formula is the formula for our Cartesian closure that tells you the positions of our of this polynomial as well as the directions at each position. So any questions about that?
Someone asked if P times Q is commutative.
If P times Q, yes, P times Q is commutative, yeah.
I was also wondering, would it be hard to write y to the y using your formula if R and Q are both y?
Let's see, if R and Q are both y, let's look at an example. Right, so if R and Q are both y, we have to stare at this for a second. Okay, so it's going to be a sum over maps from y squared into y, which there's two of them, right? Yeah, there's two of them. Y squared into y, that's really just maps from 1 to 2.
They are the 0 and 1.
Right, they are 0 and 1, so maybe I should just write the right from 0 or 1. This is going to be, it's not actually going to be a product here. These are just going to be, this is just going to be a function from, I'm going to think this through. Let's see. So yeah, so in one case it's going to be, in one case this is going to be empty, and the other case this is going to be a 1. So maybe let me just write this in two steps here, right? So it's either going to be, right. Let me just draw this out. So from y squared y, so we either have a map there or a map there, calling it 0 or 1. So in one case, for this map here that goes to 0, nothing goes to 1. And so this is an empty set. And so this should just be, whatever it is, it should just be 1. And it's some y.
One moment.
Whoa. Okay. It's not actually a sum here. Okay, so everything that maps to 0, that's just a 1. Plus, other way around. So here, actually, this is going to be a 1 here. What is Q? Q is this. So that must be a 2. Right, yes, I think, yes. So it's going to be a 2, and this.
That's the product of 2.
Yeah. It's just that, right? No?
It's supposed to be y plus 1.
Is it y plus 1?
I think it's supposed to be y plus 1.
Oh, sorry, you're right. It's the product of 2.
Yeah.
Yes. Wait. Y. Yeah. Y plus 1. Is that right? Okay. I feel like there's something off with this, but I think we're okay. Yeah. Okay. Yeah, you can check this, but yeah. Okay. Cool. So I know we started a little late, but I think I can, let's see, which of these should I still talk about? I think we'll have time to talk about most of these next time. Yeah, I guess I'll take any questions for this because this was kind of a long story, yeah.
So I have a question. What is the status right now of these wiring diagrams? Like, are they is there a formal calculus or are these kind of like heuristics? The one thing that makes me nervous
Yeah.
is that in the times example, it looks a lot like the issue you get with string diagrams when you try to mix and match,
Hmm.
you know, like two different little products. So like,
Yeah.
how do you guys think about these things? And yeah.
Yeah, there's no, right, the question was, is there, shoot, I should remember things in order to repeat them. So the question is there, like, how do we think about these wiring diagrams right now? What's the status of them? Are they formalized? Are there any issues with, like, where we have this kind of, like, different sort of wires are meaning different things, whatever it may be? And the answer is, yeah, these are very informal. In fact, I only came up with this picture of this yesterday, and so I think, yeah, I think they do, right, because I think one, there are a couple of, yeah, right, like the beauty of Poly is that it lets you change wires, right? Like depending on what state it is, you have these like different connections depending on what the state is. This wire means different things depending on what's on this wire. And there's not really an easy way to express this just by drawing it. If people can come up with an easy way to express this, we would love to see it, right? Like, I'm kind of sort of uncertain that it can be done with like pen and paper, but there is probably something you can draw, some kind of graphic that you can make. I guess it's appropriate that Evan is asking this question, but yeah, I think I'm sure there's some way of like expressing these that would actually formalize these. I would love to see that, and I think David would too. Yeah. But for now, these do give you the right answer at least. But yeah, so yeah, and of course there are other ways to actually prove that these are the right formulas. Yeah. Any other questions? Yeah.
I guess it's mainly the fact that phi sharp is a dependent function.
Yeah.
With most string diagrams, yeah, they're just normal maps, and this, if you can develop the formalism so that it's built in and understood that these are dependent functions, then it should be possible.
Yeah, I will repeat Christian's comment, which is that the tricky thing here is that phi sharp is a dependent function, right? Whatever comes in through this wire is actually going to change sort of what kind of set, like what set is it, like what this wire is. And if there were some way of like denoting that, that would be great. Of course, there's also the issue of like the fact that whatever is on this wire also changes like what this wire, or I guess that's the same. It's kind of the same thing, but also not quite. But yeah. Yeah. Yeah.
Because, I mean, yeah, these are really helpful. Like that was a great way of deriving the formulas for the humps. So if you stare at them long enough, you can see exactly how it corresponds.
Yeah. Yeah.
Should we end this round?
Huh?
Should I end this round?
Yeah, that sounds good. Unless there's other questions.